The largest object humanity has ever named was never seen, not photographed, not weighed, not confirmed. It has a name, it has a number, it has a place in every list of cosmic records ever compiled. 100 billion times the mass of the Sun. That figure appears in textbooks, in documentaries, in the caption of every image that lines up black holes by size and puts one of them at the far end of the scale, alone, dwarfing everything beside it. It gets repeated the way the distance to the moon gets repeated, as settled, as checked, as something somebody, somewhere, went out and confirmed. Nobody did. There is no photograph of Phoenix A. There is no orbit traced around it. There is no star whose motion was followed for years until its path betrayed the mass at the center. Every other black hole that holds a record was caught by one of those methods. This one was not caught at all. It was calculated. And the calculation came from a paper that was not announcing a discovery. It was writing a to-do list. Somewhere in the constellation of Phoenix, 5.7 billion light-years from the room you are sitting in, there is a galaxy at the heart of a cluster of roughly 1,000 other galaxies. Something enormous sits in its core. We are confident about that much. The question is how enormous, and the honest answer is that nobody knows, that nobody has ever known, and that the number everybody repeats came into the world as a prediction about where astronomers ought to point their telescopes next. They still have not pointed them. The number has a birthplace, and it is not a mystery. It is a paper. In January 2016, the journal Astronomy and Astrophysics published a study by Michael Brockamp, Holger Baumgart, Silke Britson, and Anton Zensus, working at the Max Planck Institute for Radio Astronomy in Bonn and the University of Queensland in Australia. The title was Unveiling Gargantua. The subtitle told you exactly what it was: a new search strategy for the most massive central cluster black holes. A search strategy. Read that again, because the entire story lives inside those two words. The paper was not reporting that anyone had found a 100 billion solar mass black hole. It was proposing a technique for figuring out where such a thing might be hiding so that other astronomers could go look. The technique itself is elegant. When a black hole at the center of a galaxy grows, it disturbs the stars around it. It scours out the core, then, as it grows further, it pulls the remaining stars inward and steepens the density profile back up. The innermost shape of a galaxy, therefore, carries a record of how much its central black hole has eaten. Brockamp and his colleagues called it a calorimeter, a device that measures consumption by measuring the heat left behind. They ran the models. They compared the results against real galaxies. And at the end, in the section where papers list what should be examined next, they named a handful of candidates worth chasing. Able 2029, RxJ 1347.5-1145, and the nuclear black hole in the Phoenix cluster, which, based on their computations, might have a mass on the order of 100 billion suns. Might, on the order of, based on our results. That sentence walked out of the paper, lost every qualifier it was born with, and became a fact. To understand what is missing here, you have to understand what it costs to actually measure one of these things. Start with the black hole at the center of our own galaxy, Sagittarius A star. It sits 26,000 light-years away, which in cosmic terms is the room next door, and measuring it took 30 years. Two teams, one in Germany and one in the United States, pointed the largest telescopes on Earth at a single patch of sky, night after night, for 3 decades. They were not looking at the black hole. You cannot look at a black hole. They were watching a handful of stars orbit something invisible, tracking their positions year after year, waiting for those stars to complete enough of their paths that the geometry became undeniable. One of those stars takes 16 years to go around once. Think about the patience in that. A graduate student joins the project. She learns the instruments, she takes her measurements, she earns her doctorate, builds a career, and somewhere in the middle of all of it, one star finishes a single lap. That is the pace at which this work moves. The 2020 Nobel Prize in Physics went to that effort, and it went to it because 30 years of watching one small piece of sky is what it takes to say, with confidence, how much mass is sitting in a place you cannot see. That is a direct dynamical measurement. Stars, orbits, geometry, it is the gold standard, and it is brutally slow. Now move outward. The first image of a black hole arrived in 2019, M87 star, at the center of a galaxy 55 million light-years away. To produce that single orange ring, astronomers linked radio telescopes across the entire planet, from Hawaii to the South Pole, and used the rotation of the Earth itself to build a virtual instrument the width of the world. The data was too large to transmit. It was flown on hard drives. That is what it costs to see one at 55 million light-years. Phoenix A is at 5.7 billion. 100 times farther. At that distance, the individual stars of the central galaxy are not points you can follow. They are a smear. There is no orbit to trace, because there is nothing resolvable to trace it with. The instrument that would be required to do for Phoenix A what was done for Sagittarius A star does not exist, is not funded, and is not on any timeline that anyone reading this will live to see. It helps to make the problem concrete rather than abstract. The region where a black hole's gravity dominates over everything else in a galaxy is called its sphere of influence. Inside that sphere, stars move because of the black hole. Outside it, they move because of the galaxy. To weigh the object, you need to resolve stellar motions inside that boundary, and the boundary is small. For Sagittarius A star, at 26,000 light-years, it spans a fraction of an arcsecond on the sky. Reaching it required adaptive optics on 8-meter telescopes and 30 years of persistence. Scale that up. Even if Phoenix A is everything it is claimed to be, its sphere of influence at 5.7 billion light-years would sit far below the resolution of any optical telescope that currently exists or is currently planned. The James Webb Space Telescope cannot do it. The extremely large telescope, when it opens, will not do it either. There is a second route. Instead of following stars, you can measure the gas, its velocities, its rotation, and infer the mass that governs it. That method has worked elsewhere. At the center of the Phoenix cluster, it runs into a different wall, because that particular core is one of the most chaotic environments known, filled with cooling filaments, jets, and a starburst violent enough to drown out the gravitational signal you would be trying to isolate. The object that would be easiest to justify observing is the object that is hardest to observe. So the number was never going to come from watching, it was always going to come from inference. The question is how much weight inference can carry. The cluster itself was found by accident, in the way most enormous things are found. In 2011, a survey team led by Ryan Williamson, working with data from the South Pole Telescope, published a catalogue of galaxy clusters detected across 2,500 square degrees of southern sky. The telescope was not imaging galaxies. It was watching for shadows. When light from the cosmic microwave background, the oldest light there is, passes through the hot gas of a massive cluster, it gets nudged. The cluster leaves a faint dent in the afterglow of the Big Bang. The South Pole Telescope was built to find those dents. One of them, in the constellation Phoenix, got the designation SPT CLJ 2344-4243 and took its place in a long list of coordinates. For a year, it was a line in a table. Then Michael McDonald, an astrophysicist at the Massachusetts Institute of Technology, took a closer look. What McDonald and his colleagues published in the journal Nature in August 2012 broke several records at once. The Phoenix cluster was among the most massive ever found, roughly 2.5 quadrillion times the mass of the Sun, containing about 1,000 galaxies and spanning more than 4 million light-years. It was the brightest cluster ever observed in X-rays. Its central galaxy was 50 times the size of the Milky Way. McDonald called it the Boss Galaxy. What is worth noticing is how the discovery actually unfolded, because it was nothing like the version people imagine. The cluster had already been catalogued. It had a designation and a set of coordinates, and it sat in a published table alongside dozens of others. Nobody had done anything wrong by leaving it there. Surveys produce more candidates than any team can follow up, and most of them turn out to be ordinary. What changed was that somebody went back. MacDonald has described the sequence plainly. They did not grasp how remarkable the object was until late in the preceding year and early in that one, when follow-up measurements in X-ray, optical, ultraviolet, and infrared came in together and finally constrained the rate of star formation. 10 different telescopes, in space and on the ground, pointed at one dent in the microwave sky. That is the shape of most modern discovery, not a moment at an eyepiece. A line in a table, ignored for a year, until someone decides it deserves a second look and assembles a decade of instrumentation to take one. Keep that in mind. It is the same shape as the thing that has not happened to Phoenix A. But the record that mattered, the one that would eventually make this whole story strange, was the last one. The central galaxy of the Phoenix cluster was forming new stars at a rate of roughly 740 per year. Hold that number for a moment because it needs a comparison to mean anything. The Milky Way, a healthy spiral galaxy in the prime of its life, produces 1 or 2 new stars in a year, sometimes less. The previous record holder among cluster galaxies, in Abell 1835, managed about 100. Phoenix was making 740. MacDonald told reporters that the rate had caught his team off guard, and that Phoenix was, in his words, crushing the record. It was also, according to everything astronomers understood about how these systems work, not supposed to be happening at all. Here is where the story splits, and where you have to hold 3 possibilities in your head at once, because all 3 have real support, and only one of them can be true. The first possibility is the simple one. The number is correct. The case for it is not weak. The Phoenix cluster is extreme in every dimension we can actually measure. It is among the most massive clusters known. It is the most X-ray luminous. Its central galaxy is a monster even by the standards of central galaxies, and the relationship between the size of a galaxy's central bulge and the mass of the black hole inside it is one of the most reliable patterns in modern astronomy. Big galaxy, big black hole. That correlation holds across a range of masses spanning several orders of magnitude, and it holds well. Extend that pattern to a galaxy 50 times the width of the Milky Way, sitting at the bottom of the deepest gravitational well in that part of the universe, and you get something enormous. Perhaps you get 100 billion suns. If this is right, Phoenix A is exactly what everyone says it is, and the only thing missing is confirmation. There is a complication, and it is worth understanding, because it decides how much confidence the first hypothesis deserves. The relationship between galaxy size and black hole mass was established by measuring galaxies we can reach, nearby ellipticals, spirals like our own, objects where somebody could trace orbits and check the answer. Within that range, the correlation is tight and dependable. Central cluster galaxies are not in that range. They are a different kind of object with a different history. A galaxy at the bottom of a cluster's gravitational well does not grow the way the Milky Way grows. It grows by eating its neighbors. Over billions of years, it consumes smaller galaxies whole, and most of what it swallows is stars, not gas. Astronomers call these dry mergers, and the distinction matters enormously, because stars added to the outskirts of a galaxy make it larger without ever reaching the center. The bulge inflates, the black hole does not. Which means that at the top end of the mass scale, in exactly the population Phoenix A belongs to, the relationship between galaxy size and black hole mass may bend, or flatten, or break entirely. We do not know, because we have almost no direct measurements up there to check it against. And that is the position anyone extrapolating finds themselves in. You take a rule calibrated on the objects you can measure, and you apply it to an object that grew by a mechanism the rule was never tested on, in a mass range where nothing has been confirmed. That is not a reason to dismiss the number. It is a reason to remember that it is a projection, made in the one regime where the tool is least trustworthy. The second possibility is that the number is not a measurement of what is there, but a calculation of what would have to be there. This is a subtle distinction, and it is the most important one in this entire video, so let me make it concrete. The Brockamp method works backward. It looks at the observed structure of a galaxy's core and asks, how much would a black hole have needed to grow in order to produce this shape? The answer it returns is not, the black hole weighs X. The answer is, if this model of core evolution is correct, and if the feedback energies are what we estimate, and if the accretion efficiency falls in this range, then the black hole would have to be around X. Every one of those conditional clauses is a place where reality can diverge from the model. And the paper itself was careful about this. The authors noted openly that their models were not fine-tuned to match the properties of the Phoenix central galaxy or its exact redshift. They observed that changing an assumption about the galaxy's size changes the mass you have to invoke. They were doing what good scientists do, which is showing their work and marking the joints where it might break. None of that survived the journey to the internet. The third possibility is the uncomfortable one, and it comes from theory rather than observation. In 2009, Priyamvada Natarajan, an astrophysicist at Yale University, and Ezequiel Treister, then at the European Southern Observatory in Chile, published a paper in the monthly notices of the Royal Astronomical Society, asking a question nobody had properly answered. Is there an upper limit to how massive a black hole can get? Their answer was yes, and their reasoning was that black holes destroy their own food supply. A black hole does not simply swallow matter. As gas spirals inward, it heats and it radiates, and past a certain point, the outward pressure of that radiation is strong enough to push the remaining gas away. The object clears out its own neighborhood. It starves itself. Natarajan and Treister worked through the physics of that self-regulation and concluded that the ceiling should sit somewhere around 10 billion solar masses. 10 billion. Phoenix A is supposed to be 100 billion. 10 times a theoretical limit is not a rounding error. It is the kind of gap that, in any other context, would send everyone back to check the arithmetic. Now, that limit has moved. In more recent work, Natarajan and colleagues have examined the ultramassive population more carefully and placed the practical ceiling considerably higher, in the neighborhood of 100 billion solar masses, which sounds like the problem resolves itself. It does not resolve itself. It gets stranger, because if the maximum possible mass for a black hole is around 100 billion suns, and the single largest black hole anyone has ever claimed to identify weighs in at almost exactly 100 billion suns, then one of two things is true. Either we got extraordinarily lucky, spotting the champion of the entire observable universe on our first serious attempt, sitting precisely at the ceiling, or the number we assigned it came from the same theoretical framework that produced the ceiling, and we have been admiring the reflection of our own assumptions. 3 hypotheses: a correct measurement, a conditional model mistaken for a result, or a theoretical prediction that circled back and confirmed itself. There is a way to tell them apart. Somebody has to go and look, and here is the part that changes everything. Somebody already did, not at Phoenix, somewhere closer, and what they found should have stopped this conversation years ago. There is a galaxy called Holmberg 15A. It sits at the center of a cluster called Abell 85, and it is close enough to reach. For years, the black hole at its core was estimated the way Phoenix A is estimated, indirectly, through the dynamics of the galaxy and the cluster around it, through scaling relations and modeling. Those estimates were published, they circulated, and the largest of them put the mass of Holmberg 15A's central black hole at 310 billion solar masses, 3 times larger than Phoenix A, the undisputed heavyweight of the known universe, by any list you cared to compile. Then, in 2019, a team led by Kianush Mehrgan at the Max Planck Institute for Extraterrestrial Physics in Garching decided to measure it properly. They used an instrument called MUSE, mounted on the Very Large Telescope in Chile, to capture high-resolution spectra across the galaxy's central region. Then they built orbit-based dynamical models, reconstructing the actual paths of the stars, and asked what mass at the center could produce the motions they were seeing. The answer came back at 40 billion solar masses, plus or minus 8. In their paper, they described it as the most massive black hole with a direct dynamical detection in the local universe. 40, not 310. The moment somebody actually looked, the number fell by a factor of nearly 8. And it did not stop there. In 2025, a second team, led by Emily Leopold and Chungpei Ma at the University of California, Berkeley, working with Jonelle Walsh, returned to the same galaxy. They used a different instrument, the Keck Cosmic Web Imager on the Keck 2 telescope in Hawaii, and a more sophisticated modeling approach that allowed the galaxy to be triaxial rather than assuming symmetry. The difference between those two approaches sounds technical. It is not. When you model a galaxy, you have to assume a shape. The 2019 work assumed axial symmetry, which means treating the galaxy as though it were symmetric about a single axis, like a spinning top. It is a reasonable simplification, and it makes the mathematics tractable. The 2025 work allowed the galaxy to be triaxial, with 3 unequal axes, which is closer to what these enormous ellipticals appear to be in reality. Change the assumed shape, and you change how you interpret the motion of every star in the model. Stars that looked like they were orbiting fast because of a heavy center might instead be moving along elongated paths in a lopsided galaxy. The number came back again, this time at 22 billion solar masses, half of the direct measurement, a 14th of the original indirect estimate. Sit with that sequence: 310 billion from inference, 40 billion from the first careful look, 22 billion from a better one. Every single time a human being pointed a real instrument at that galaxy and did the hard work, the monster got smaller. This is not a scandal. Nobody was dishonest. The indirect estimates were the best that could be done with the information available, and they were published with appropriate uncertainty by careful people. What happened to Holmberg 15A is exactly what science is supposed to do. A rough answer gets replaced by a better one, and the better one gets replaced again. But it tells you something about the class of number that Phoenix A belongs to. Phoenix A has never had its 2019. It has never had its 2025. It is still sitting at the first stage of that sequence, the stage where the estimate is large and the evidence is a model, and it has been sitting there since 2016, while its number gets copied from one list to the next, as though it had graduated. There is one more piece of context that should make you uneasy. A survey of the field, written for the astronomical community, noted that in the local universe, the 2 largest black holes confirmed by direct dynamical measurement come in at 15 to 20 billion solar masses. 15 to 20 billion, that is the honest, measured, confirmed ceiling of everything we have actually verified. Every number above that, including the one in the title of this video, lives on the other side of a line that nobody has crossed with an instrument. If you have made it this far, you are the kind of person who wants the number checked before believing it. That instinct is the entire reason this channel exists. We do not repeat what everybody repeats. We go and find where it came from. Subscribe and stay with us, because the strangest part of this story is still ahead. Return to the thing McDonald found in 2012, because it has been waiting this whole time. 740 new stars a year. To understand why that is a problem, you need to understand what a black hole of the claimed size is supposed to do to the galaxy around it, and the answer is, it is supposed to sterilize it. In a cluster like Phoenix, the hot gas at the center should be cooling, condensing, and falling inward. Left alone, it would collapse into vast quantities of new stars. Astronomers call this a cooling flow, and for decades they expected to find cluster after cluster blazing with new star formation. They did not find it, almost nowhere. The reason is the central black hole. As it accretes, it drives jets and outflows that reheat the infalling gas, interrupt the collapse, and shut the process down before stars can form. The bigger the black hole, the more violent this feedback becomes. In the most X-ray luminous clusters, that heating is powerful enough to erase even the most pronounced structures at the core. This mechanism is why cooling flows almost never produce the starbursts they should. It is one of the more satisfying explanations in modern astrophysics, because it links the smallest structure in a galaxy to the fate of the largest. Now apply it to Phoenix. The Phoenix cluster has the most luminous X-ray core of any cluster known. Its cooling flow is enormous, with estimates of the gas raining inward, reaching thousands of solar masses per year. If there is a 100 billion solar mass engine at the center of that galaxy, its feedback should be among the most ferocious in the universe. Star formation there should be effectively zero. Instead, the Phoenix cluster is the most fertile cluster ever observed. Roughly 30% of the cooling gas is converting into stars. In a typical cluster, that figure is around 1%. Phoenix is running 30 times hotter than it should, in the one place where the break is supposed to be strongest. There are only a few ways out of this, and every one of them costs something. Perhaps the black hole is genuinely that large and is simply between meals. Feedback is episodic. Jets switch on and off over millions of years, and it is possible we are watching during a quiet phase, a gap in the cycle when the gas has been left alone long enough to collapse. This is the mainstream reading, and it may well be right. Perhaps the feedback is there but poorly aimed, escaping along axes that miss the densest gas, so that the energy is released without doing the job it usually does. Or perhaps the engine is not as large as we have been told. Perhaps the reason the Phoenix cluster is forming stars like nothing else in the observable universe is that the thing at its center is not the largest black hole ever found, and never was. Notice what all three explanations share. Not one of them can be settled by argument. Every one of them dissolves the moment somebody measures the mass directly, and not one of them can be resolved until somebody does. The most cited number in popular astronomy is attached to the one object where the surrounding evidence quietly refuses to agree with it. And there is a detail here that deserves its own moment, because it inverts the whole picture. The Brockamp method does not weigh a black hole by watching it. It weighs it by reading the feedback energy the cluster has absorbed over its lifetime, and converting that energy into a mass the black hole must have swallowed to release it. Follow the logic in a circle. The Phoenix cluster releases prodigious amounts of energy. Prodigious energy implies prodigious accretion. Prodigious accretion implies a prodigious black hole. The calorimeter reads the heat and returns 100 billion suns. But the same energy that produces that estimate is the energy that is failing to stop the star formation. The cluster is loud, and the loudness is what the number is built from. The cluster is also fertile, and the fertility is what the number cannot explain. One observation feeding two conclusions that point in opposite directions. That is not a flaw in anyone's work. It is a signal that the system contains something we have not accounted for. In science, a contradiction of that kind is not an embarrassment. It is a location. It tells you where to dig. There is a version of this story that is disappointing, and there is a version that is not. Which one you get depends on what you thought the point of astronomy was. If the point was to collect superlatives, then this is a letdown. The biggest thing in the universe turns out to be a conditional clause in a 2016 paper about search strategies. Wearing a crown, nobody awarded it. But that was never the point. Consider what actually happened here. A group of researchers in Bonn and Brisbane built a method for reading the history of a galaxy's core out of the arrangement of its stars. They used it to say, "Look here next." Someone else, using a telescope in Chile, took a different galaxy off that same kind of list and found the monster was a quarter of its reputation. Someone else again, with a telescope in Hawaii, found it was half of that. Every step in that chain is a person choosing the slower, harder, less satisfying path, choosing to go and check. And the number for Phoenix A is not wrong. It has simply never been tested. It is a hypothesis that has been standing patiently in the queue for a decade, waiting for an instrument that can see 5.7 billion light-years into a galaxy's heart and count what is orbiting there. That instrument may be built in your lifetime. It may not. Until then, the largest object in the known universe remains a claim. There is something almost unbearable in that. We have mapped this thing, named it, ranked it, animated it swallowing solar systems, and placed it at the summit of every scale we have ever drawn. And underneath all of it there is a model, a set of assumptions, and a sentence that ends with the words, "might have a mass on the order of." Somewhere in the constellation of Phoenix, the thing itself is doing whatever it has been doing for billions of years, entirely indifferent to what we have decided about it. It is not the biggest, it is not the smallest, it has no rank. Rank is something we invented and then forgot we invented. The universe does not hand us its records. We assemble them, out of inference and patience and instruments that are never quite good enough, and then we live inside them as though they were the thing. We named the largest object in existence before we ever saw it. That is either reckless or magnificent. It might be both. Thanks for watching, and I'll see you in the next one. One more thing before you go. Everything in this video came from 4 papers and a decade of people refusing to accept the easy answer. If that is the kind of story you want more of, subscribe. There are more numbers out there that nobody has checked.